Okay, we're going to continue on here, chapter 11, and we got into organicness here. So we got into organic chemistry last time, and organic chemistry, as I mentioned, kind of the basic setup of those type of compounds are going to be our carbons attached to carbons, and essentially attached to those carbons are going to be hydrogens. One of the important things to remember is essentially carbon will need always 4 bonds when you have it in a structure. And in a lot of cases, if there's no other elements involved, then you basically will use hydrogen to get it to 4 bonds. So a couple important things to remember, as we talked about last time. Again, carbon should have more than 4 bonds, but will need 4 bonds. And hydrogen, like, with just but we talked about a couple different types of formulas. This is the expanded structural formula. And that basically is kind of like a Lewis structure where you basically draw out all of the hydrogens that are involved. We can also kind of shorthand this one, which is known as a condensed formula. And in the condensed formula, it's pretty much like the other one, except that we do not draw out the hydrogens. So this is the condensed formula. And there's also the line structure that we talked about, which is pretty bare minimum. Again, we don't put carbons in there. We don't put hydrogens listed. We only put anything that's pretty much other than those two things that are other than a carbon or a hydrogen. It would be the only time we do that. Remember that pretty much anywhere the line sort of ends is technically a carbon, and anywhere where two lines come together is going to be a carbon. And again, each of those carbons will have enough hydrogens to basically get it to 4 bonds. So this guy at the end has really only one line coming in. So it would actually have, again, 3 hydrogens. The carbon technically in the middle there has a line on each side, which is 2 bonds, which means it would need 2 hydrogens. And the guy at the end here on the right also only has one line coming in, which means, again, technically it would have 3 hydrogens. But again, in line structure, we pretty much don't put any of those things in. It is just, again, sort of a bare minimum type of structure. We talked about alkanes. Alkanes are the simplest organic molecules. They have essentially a functional group that is carbon-carbon single bonds. So carbon-carbon single bonds are basically alkanes. Alkanes, again, are the really basis of everything in terms of naming for all the other types of organic molecules. They have a general form of CnH2n plus 2, where N is the number of carbons. So if we had 1 carbon, 2 times 1 is 2 plus 2 would tell us we have 4 hydrogens, and that is methane, ANE. We had 2 carbons, 2 times 2 is 4 plus 2 is 6, and we would have what is known as ethane. We have 3 carbons, 3 times 2 is 6 plus 2 is 8, and that would be propane. And you could continue on through those first 10 that we talked about. And a reminder that, as I mentioned last time, since everything really does sort of go back to those first 10 names, it's really important to get an understanding of the 10 names and the formulas and how many hydrogens and carbons they have, because again, everything is just going to kind of come back to those sort of names. We also talked about the idea of cycloalkanes, and cycloalkanes are also single bonded alkanes with single bonds. The difference is they really kind of form a ring type structure, and they have a general formula of CnH2n. Remember, as we talked about, kind of in organic chemistry, whenever you sort of add a bond between 2 carbons, for example, you basically need to sacrifice a hydrogen on each of those carbons. So you lose 2 hydrogens. So that's why when the sort of ends of these guys come together to make that bond and make it a ring structure, we will sacrifice 2 hydrogens, so that is why it's not at the end there H2N plus 2, because we kind of lose that plus 2 hydrogens when we come together. These are typically the ones that are drawn mostly in line structure most of the time. These are sort of like our geometrical shapes. We have our triangle, right, our square, our 5-member ring here, and our 6-member ring here. And pretty much with these, all we do is just add cyclo to the beginning of the name. So this would be 1, 2, and 3 carbons. That again is based off of propane. So this would be cyclopropane. This has 1, 2, 3, 4 carbons. That would be cyclobutane. That has 5 carbons, 1, 2, 3, 4, and 5. That's going to be cyclopentane. And lastly, this guy's got 6. 1, 2, 3, 4, 5, and 6. That's going to be cyclohexane. You could also, if you wanted to, still draw like sort of condensed structure for these. And basically what you do is something like this, just kind of, and just put your appropriate hydrogens there. We'd have something like that as well. Any questions on any of that stuff we talked about there last time? All right, let's continue on our journey here. So take a moment here for each of these, although I just did 2 of them. For the other ones, I had to give the names of those guys. Okay, so let's take a look. And again, pretty much as we'll talk about when you go to name things, these are a little straightforward ones, but always pretty much what you want to do is count up how many carbons you got. What is the longest sort of run of carbons that you got going on? So here we got 1, 2, 3, 4 carbons. Everything else is hydrogens there. So that should be our friend butane, as they are all single bonded. A reminder, as we talked about last time, although in sort of a condensed formula there, it does appear that perhaps the hydrogen's in between those carbons, but again, reminder that the connection that you have, again, is our carbons to carbons. And again, those hydrogens are on the outside. So that again is the way it actually is put together, even though the condensed structure sort of implies that maybe the hydrogens are in the middle or something like that. And again, that's how we get to each of those things. That's a CH3, so that's a CH3. That's a CH2. That's a carbon and 2 hydrogens, or CH2. And at the end here is a carbon and 3 hydrogens, which gives us our CH3. So just keep that in mind. Obviously, here we have a ring type structure, which means it is cyclo, and they're all single bonded. And again, if we just count up our carbons, that is 3. 3 is based off of propane if it's just a straight chain, but here in this sort of cyclo structure here, this would be cyclo, again, propane. Coming down this way, we got 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5, 6, 7, and 8. 8 is going to be octane here. And lastly here, we have the one we just saw there when we were just talking. That is going to be our 6-member ring. And again, all those are carbons. So really 6 carbons is hexane, all single bonded. And again, we put cyclo at the beginning of it, as it is a ring structure. Any questions on that there? Then let's talk about what happens when we actually have something else attached. And when an alkane has 4 or more carbons, the atoms can be arranged side by side, which is called branch chain. Our substituent is attached to the carbon chain. So as I mentioned before, what sort of makes things different, sort of organic compounds along the way, is we kind of replace some of the hydrogens with basically other elements perhaps. And different arrangements will also give you some different sort of organic compound. Now, when we look at an alkane and we talk about a hydrocarbon, and just to sort of reiterate here, that if we had something like we were just looking at there, this is what is sometimes referred to as a saturated hydrocarbon. And what the idea of saturated means is basically each of those carbons in that particular compound has the maximum number of hydrogens it could have, basically. And that's what makes it saturated. Now, when something is unsaturated, it means that basically it doesn't have the maximum number of hydrogens that it should have. And what that means is most likely you don't have all carbon-carbon single bonds. So you have maybe a double bond, maybe you got some other element attached. So a saturated hydrocarbon is one where pretty much all you got is carbons, all single bonded, and you pretty much have the maximum amount of hydrogens that's present. For example, when we get into double bonded ideas here, when you have a double bond, missed the hydrogen there. Fix that up there. And we put in everything that's here. When we look at this, these two carbons here do not have the maximum number of hydrogens because, as we just talked about, to make that double bond, you got to lose a hydrogen on each one. And that is what is sometimes referred to as an unsaturated hydrocarbon. Unsaturated again means that basically we just don't have the maximum number of hydrogens that are there. Remember that we can have a straight chain sort of connection, which everybody just runs side by side. We can have like a tree, sort of a long straight chain, and off of that, maybe some branches that occur, some other things attached to the longest part of the molecules, which is known as branch chain. So when we talk about certain compounds, um, we have what are sometimes referred to as isomers. And what isomers are, structural isomers, they are basically a compound or basically two compounds or more that have the exact same molecular formula, but they are actually connected differently. And they will actually have a different sort of name. Now, for example, if we look at this guy here, which is our 4 carbons in a row, which is our friend butane. It's got 4 carbons and 10 hydrogens if you count it all off. Now, if you draw basically what is here in this ball and stick sort of model, you got something that looks like this. And you also have basically C4H10 in both of those arrangements. Now, they are connected differently, and they actually have different names. This guy here, for example, is obviously 4 carbons in a row. This is what is known as butane. Now, when we get to this guy, we actually will get a different name. And we're going to talk about that right now, I think, in just a second. Actually, I'll do this, I think. So if we take a closer look at that second guy, after obviously we have this guy here. When we go to name this, again, the longest carbon chain is basically just 4 carbons straight back to back, basically, which gives us our butane that we saw. When we look at the other one that was there that we had drawn, we have this basically. When we look at the second one, What is the longest continuous carbon chain that we have here? How many carbons in a row without backtracking, going one way and going till you hit a dead end? It's only 3 in this case, right? And you can actually get 3, by the way, couple different ways. You could just go left to right and you hit a dead end, and that's 3 carbons. You also can, by the way, if you wanted to, you could go straight and then up, and that also would be 3 as well. It doesn't really matter which way you go. So one of the first things that you want to do when you're trying to name something in organic chemistry is, again, you always want to look for the longest continuous carbon chain. And again, it may not always be the straightest one that just goes straight across. It may go kind of straight, then kind of come up, kind of come over, maybe up again and over again. But the only rules, and I might have mentioned this last time, is this: you have to kind of start in one direction and go until you hit a dead end. You can't backtrack or anything like that. So you got to just keep rolling until you hit a dead end. So in this case, that's basically 3 if we go straight. It's 3 if we go left and then go up. And by the way, just for good measure, it's also 3 if we start on the right here and then go up. It doesn't matter whichever way you want to pick. So what we're going to do is, my recommendation usually is, if you got one that is straight across just in a row and that's equal, you might as well roll with that. And when we name these alkanes, and we're going to name them using the IUPAC way of naming, which is that International Union of Pure and Applied Chemistry, when we find the longest carbon chain, that's going to be really kind of like the base of our name. So in this case, this is 3 carbons, which means 3 carbons that are all single bonded is our friend propane. And that is the base of this particular name. Now, when we look at this, there is something that is attached there that has a carbon, for example, and is not part of that longest carbon chain that we just counted. And that would be this guy right here, which is this guy right there. That is not part of the longest chain, and that is what is referred to as a group because it's not part of the longest carbon chain. More specifically, this is sometimes referred to as a alkyl group, and that is because it's a carbon-containing group. So we also need to name this guy. And how we go about naming this guy, as I mentioned, is probably not surprising. It is based off of the first 10 alkanes. So when I look at that little group that's attached, how many carbons does it have? It has 1 carbon. And if you think about our first 10 alkanes, 1 carbon looks like this guy right here, right? This is our friend methane, right? 1 carbon. Now, the group that I highlighted here is a little different to methane. What is different between it and methane? Yeah, it has 1 less hydrogen, right? And the reason it has 1 less hydrogen is, if I try to stick methane onto that carbon, so I'll just draw that carbon right here. So if I had that carbon basically here, and we got our hydrogen, and I just tried to stick methane onto it, right? This carbon right here would end up with how many bonds? It would end up with 5 bonds, too many, yeah? So remember, carbon could only have 4. So if I just took that and tried to stick that methane right on there, just the way it is, I would end up with something that looks like this. Carbon, 1, 2, 3, and 4. And now that carbon has too many bonds, right? It's got 5 over the octet rule there, right? Not so good. So what these groups are, or these alkyl groups are, they are basically your alkanes, but they are missing a hydrogen. And by missing a hydrogen, that allows them to be able to connect in and not have too many bonds. So that is methane. And what we have here is actually a carbon with only 3 hydrogens. and that is where it's going to be able to connect into the other carbon that's there. Surprisingly enough, this is not methane. So instead of methane, we drop the ANE, and these is called an alkyl group, which means this guy right here is known as a methyl group. Yeah. YL at the end, based off of methane. By the way, if I had two carbons instead of ethane, it would be a ethyl group, right? If I had three carbons attached as a group, it would be a propyl group, and so forth as you go through it. So when we look at these sort of alkyl groups and they're carbon based, we basically name them off those first 10 alkanes. We drop the sort of last part of it, and we do put the YL at the end of it. So this is actually a methyl group. Let's come here, methyl. And this would be, as you can see there, did it have a name? Did not did. This is going to give us the location of where we could put this. This is carbon 1, this is carbon 2, and this is carbon 3. So this is going to be 2-methyl propane. The location of basically the group is indicated by a number, and the last part of the name is basically the longest continuous carbon chain. Now, these two guys, although they do have the same formulas, they are connected differently, and we can verify that by them both having basically different names. And again, these would be isomers of each other. Even though they have the same formula, they are connected differently, and they are different things. They will have different properties because of the way they are connected to each other. Question on that there. Yeah. You do not, and give me like 5 minutes, and we'll talk about the way to name all that, and we'll talk about all the weird rules that you have to follow in just 1 second. Yeah. The 2 is really about the location of where you have that group on the longest carbon chain. As we'll talk about in just a second, basically the naming part in organic chemistry is all about telling people exactly where you can find everything. And kind of where you can find everything is based on your longest carbon chain. It's like, okay, I got this really long chain of carbons. And if you go to like carbon 2, you'll find this guy hanging out there. If you go to carbon 4, you'll find this guy over there. So it's all really about kind of telling everybody where everything's located. And we're going to talk about the rules here in just a second, and we'll get back to it here. But let's talk a little about substituents. And like I mentioned before, substituents are these groups that are attached to the longest carbon chain. And they really are, if they are carbon-based, referred to as alkyl groups, and they are based on how many carbons there are. And again, we dropped the last part of the alkane name and put the YL there. Now, if you have a halogen, they're named a little bit different, and halogens, which are group 7 on the periodic table, do find their way into organic chemistry a lot. So fluorine is known as fluoral, chlorine is known as chloral, bromine is known as bromo, and iodo there for iodine. So that is how you name halogens if you have halogens attached: fluoral, chloral, bromo, and iodo for iodine. Here again is our some of our groups here and how you go about naming it. That basically is a 1-carbon group. That's a methyl group. That's a 2-carbon group, which is an ethyl group. This is a 3-carbon group, which is a propyl group. Now, a very historical sort of name is this guy right here. That is also a 3-carbon group, but that is what is referred to as an isopropyl group. So when we look at carbons, for example, we could actually classify the carbons as one of 3 types of classifications. There are primary carbons, there are secondary carbons, and there are tertiary carbons. So we can look at carbons and identify what type of carbon it is, either primary, secondary, or tertiary. Obviously, primary, secondary, and tertiary. And the way you could do this is a couple ways, but personally, I think this is the good way to go. Let's just say we had, let's see what I can do here. You, won't draw out the hydrogens over here. I'll just kind of shorthand it here. Save a little room. All right, so how do you know if your carbon you're looking at is a primary carbon? Well, primary symbol is what number? 1. So basically, you look at the carbon you're interested in, and you count up how many carbons are directly attached to it. So for example, if I look at this carbon right here, how many carbons are directly attached to it? 1. That is what we like to call in the business there a primary carbon because it's directly attached to 1. Secondary, the number for secondary is 2. So if we go to this carbon, say right next door, how many carbons are directly attached to that guy? There is 1 right here and 1 on the other side, right? So that is 2 carbons that are directly attached. There's a bond right there. There's 1 attachment to a carbon, and there's a second attachment to a carbon. And that is 2. That means that this carbon right here is a secondary carbon. I imagine you know where I'm going with this on the last one here, but let's do it. That is a tertiary carbon, right? Right there. Our tertiary means 3, basically, right? So if I look at this carbon right here, how many carbons? Actually, I overcarboned it. Let me actually do this, so we'll make it better. Let me undercarbon it now. There we go. How many carbons are directly attached to that? That is now 3. I kind of get rid of the other carbon there. So we have 1 carbon right there, right? 2 carbons and 3 carbons. Remember, the attachment there is to the carbons, and that would be a tertiary carbon. Any questions on that? I personally think the best way to do it is to count how many carbons are directly attached to it. Some people teach you to count how many hydrogens there are. So if there's like 3 hydrogens, it's primary. If there's 2, it's secondary. And if there's like 1 hydrogen, it's tertiary. But frankly, I just think carbon gives you the right number off bat. I have 1 carbon attached, primary, 2 carbons attached, secondary, and 3 carbons attached, tertiary. So I went into this because when we look, for example, at propane here, which is what these 2 guys are basically coming from, if we draw out our propane, the carbon on the left-hand side there, this carbon right here, primary, secondary, tertiary. How many carbons are directly attached to it? 1, so it will be primary, yeah? Go with counting carbons because 1 carbon means primary, 2 carbons means secondary, right? 3 carbons mean tertiary. This guy right here, how many carbons are directly attached to that one? 2, that would be a secondary. And the guy over here is 1, which would be a primary, right? Yeah. So when we have propane like this, we actually have 2 types of carbons. We have primary carbons, which are on the end. And if you get rid of a hydrogen on like the left-hand side or the right-hand side carbon, either of those primary carbons, you will get what is referred to as just a regular old propyl group where it attaches at the primary carbon. Some people even call it N-propyl for like normal propyl group. Sometimes they'll call it. But if you take off a primary hydrogen and allow it to connect in through that primary carbon, you'll just get a regular old run-of-the-mill propyl group attached. Now, if you take off a hydrogen here at the secondary carbon, that is where it's going to attach. It's actually going to attach right there. And it's going to actually make the attachment happen actually at that middle carbon, which is a secondary carbon. That is a special historical group, an historical name that people still use today. That is known as isopropyl. And again, isopropyl is sort of this arrangement. The iso part of it, I guess is the way to say that. The iso part of it is like a CH3, CH3 sort of run. That is sort of always what like an iso sort of group is. Same thing here. If you take butane and remove a hydrogen from one of its primary hydrogens, it will attach at the end, and you'll get a plain old run-of-the-mill butyl group. But if you take out this guy right here and let it attach there, actually, we're taking out still this one here, it will still make a iso group there, but this is known as isobutyl, as it is basically has one more carbon attached, which is the butane part of it. So there is like isobutyl, there's isopropyl. I think those are two very common ones. There's also, sometimes this is referred to, some of these, as sec-butyl. And sec-butyl would mean probably it's attaching at the secondary carbon. Yeah, so that's what secondary makes me. There's also a T-butyl group. You had to guess the T means it's attaching on what carbon? Tertiary carbon is where that's going to be attached. So there's some of these kind of historical sort of group names that you sometimes come across. And the difference really in terms of why it has sort of a different name and a little different arrangement is where the attachment is going to come to the main chain. Is it going to be a primary carbon? Is it going to attach at a secondary carbon? Will attach at a tertiary carbon? Any questions on that? I would say for us, probably the isopropyl, isobutyl are probably the two funky ones that you might come across probably in this class. Again, we have our halogens there as well, our fluoro, our chloral, our bromo, and our iodo. Any questions sort of on the groups here that are attached? All right, so now that we understand that we have these groups, most of them are really based off of those first 10 alkanes. Let's actually talk about how we actually go about naming something so that we know if we maybe did draw different isomers or not. So I'm going to roll here. So let's just start with the very first thing you always want to do, which is count the number of carbons in the longest continuous chain. So that's pretty much where you want to start. You want to look at your structure. You want to, again, do all your options. So again, they may not always be the straightest option. You want to do any options you have. You want to, again, not backtrack, go one way and stop, and you want to find the longest continuous carbon chain. Once you do that, that will be the base of your name. And it should probably match one of those first 10 alkane names. So should really match one of those first 10 alkane names. Once you've identified the longest continuous carbon chain, the next thing that you want to do is find all the groups that are attached to that chain. So longest carbon chain, frankly, you can highlight it, throw a box around it. It's a good way to do it, and just figure out what else is there that you might need to name. The next thing that you want to do is, once you've identified your groups, you know your longest carbon chain, you want to number the carbons in that longest chain. Now, the way that we number the carbons, which I think was a question a second ago, it doesn't matter. You could go left to right, go right to left. You should check both ways. The way we always want to number the carbons in an alkane is to give the groups that are attached the smallest numbers. So we want to number those carbons in the longest chain, whichever way that will give actually the groups here in alkanes, the stuff that's attached to that longest chain, give them the priority in terms of the smallest number. Once you do that, we're going to name it, starting with the groups in alphabetical order, regardless of the number. And then end with the name of our longest carbon chain. Now, a couple of other things that we do when we name things. If you have a letter that goes into a number, we use a dash. Or if you have a number that goes into a letter, we put a dash between them. Now, there will be situations where you might have two numbers. We actually put a comma between the two numbers. So these are a couple other things we sort of do to make it look pretty and all those things. These are the basic rules for how to name the IUPAC way alkanes, basically. Yeah. And these are how you would name alkanes that have groups or substituents attached to it. First off, any questions on that there? So let's take a look at one here to see how we go about doing that. So let's see here. Let me just draw something. I don't know. Yeah, we'll throw a CL there. Why not? Okay. So let's say we have this guy. Whatever I just drew there. Let's go with it. Hope for the best. All right. So the first thing we want to find, right, is our longest continuous carbon chain. So again, we do not want to backtrack. You got to start in one direction and go until you hit a dead end. So take a moment and figure out here, what is my longest continuous carbon chain? Again, does not always have to be the straightest. Yes. All right, so let's see. And again, you do want to perhaps check all your options. So if I just go straight across, that is 1 carbon, 2 carbons, 3 carbons, 4 carbons, 5 carbons. So that's pretty long. If I go straight across, 1 carbon, 2 carbons, 3 carbons, 4 carbons, and then go up 5 carbons and 6 carbons. So that's more going in that direction. I could also trying all my options here. 1 carbon, 2 carbons, 3 carbons, 4 carbons. So that's less. So it looks like after exhausting all my options, and again, will not always be just the straightest one, which it isn't in this case, it appears that our longest carbon chain is actually 6. It goes straight, goes up, and then hangs a right. Yeah. Any questions on that there? So you can put a little box around it, or if you highlighted it like I did, that wouldn't be too bad. So by figuring out our longest carbon chain, which is 6 in this case, they're all single bonded, which means 6 carbons. The base of this name should be hexane, right? Because that's what our 6 alkane is. Now, there are a couple of things that are on this that basically are not part of that chain. We have this guy right there, and we also have this guy right there. Those are groups that are attached to this, and those groups are going to have some names. So this is chlorine, which means this is going to be a chloral group, right? And this is a 1 carbon group, which means instead of methane, this will be our methyl group, right? So that's our methyl group. Any questions on any of that there? All right, we're almost ready to sort of name this thing. The next thing that we want to do is we want to number that longest carbon chain of 6. Frankly, you usually only have 2 options as to how you can number those carbons. So if I go through this and number the carbons going left to right, that would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, that would be carbon, I don't know, I could count, but not right. Carbon 5, and that would be carbon 6. The other option would be to start numbering up on top and going right to left is your other option. And these are your 2 options in this case. I'll go blue on this. 1 carbon, 2 carbons. This would be carbon 3, carbon 4, carbon 5, and carbon 6. First off, any question on the numbering? Just basically going to take one way and then number it the other way. So what we're looking for is where, in the case of alkanes, our groups are sitting on what carbon is basically why we're numbering things. So since I have blue here, if we go in the blue direction, that means that if I went to carbon number 3 and carbon number 5, I would basically have groups there, right? At carbon number 3, I would have the methyl group. At carbon number 5, I would have the chloral group, right? Now, if I went the red direction, which is left to right, my chlorine group would actually be at carbon number 2, and my methyl group would be at carbon number 4, right? It's hanging off right there to that guy, and right here. First off, any questions on that? Now, it is as simple as this. Looking up the first number, which one's smaller? The 2. That's the winner. It's always the smallest, yeah? So it's not more complicated than that. It's like, that's the smaller number. I'm rolling with it. I don't care about the second number. Really, the first number is kind of the one that's most important. So here, this is going to be the smallest number, which means the correct way I want to number this chain is going to be in the red direction. That means really at this point, I don't need any of the blue numbers. You can leave them, scratch them out, erase them, whatever you want to do. But we're not going to go in that direction because going in the red direction here is going to give us the smaller numbers. Any questions on that? That means that when I look at my group here, at my chloral group, it again is on what carbon? 2. So that is what is known here as a 2' chloral group. A dash between the number and the letter, yeah? So between the number 2 and the letter C, we lay up a dash. My methyl group is at what carbon? Yeah, so this guy is basically a 4' methyl group, yeah? Any questions on that there? We're ready to finish our name here, which is we're going to put our groups in alphabetical order, regardless of number, and also regardless if there is a prefix like di or tri in the name, and I'll show you one in just a second. We actually ignore that. So when we look at the groups, that is C, that is M. Which one should come first alphabetically? C, right? So this is our friend here. I'll start right about there. 2' chloral. Again, we need a dash between the letter and the next number, which is 4. One more dash between the number and the letter. Methyl, squeezed it in. Hexane here. So this would be 2 chloral, 4 methyl hexane. Questions on that there? So again, we want to find the longest continuous carbon chain. That's going to be the base of the name. We then want to find everything that's not part of that chain, identify what groups we got going on. We then want to number the longest chain to whichever way will give those groups the smaller number always. Pretty much in organics, always smaller wins. Yes, so the smallest number is really what you're always shooting for. And then again, we want to put them in alphabetical order. Any questions on that there? Now, let's say I had a number of ways. You could just go, if you like, straight across is 4. You could also go straight and then up, which would be 4. Believe it or not, you could also go that way, and that was 4 as well. Again, it really doesn't matter which way you choose. They all should come out the same name, regardless of what 4 you kind of choose in this case. But once again, as I mentioned before, I would personally roll with maybe the straightest is sometimes easier to see everything. So if we go straight across here, we got 4 carbons, all single bonded. 4 carbons is based off of our friend butane, right? We have this carbon group and this carbon group, which are groups attached to this chain, but not part of it. Each of those are 1 carbon groups, which means each of them are a methyl group, right? So now we need a number. I go left to right. 1, 2, 3, 4. I go right to left. 1, 2, 3, 4. Doesn't matter in this case which way I go. No, because no matter which way you go in this case, you end up with a 2 and a 3, basically, right? So it's your call. It doesn't really matter. You could do with that because they're both the same group. So we definitely have, we'll just go, it don't matter, we'll go in this direction. I'll call that one 2, that one 3, right? Now, in this particular compound, not necessarily on the same carbon, but in this particular compound, there's how many methyl groups? 2, right? And because of that, these 2 will then become a dimethyl because there are 2 methyl groups in the compound, not on the same carbon. They could be on the same carbon. They don't have to be on the same carbon. By the way, if I had 3 of them in that thing, there would then be a trimethyl, right? If I had 4, it would be a tetramethyl, but that's probably all you would get. Now, we do need to still give the number where we locate these things. And in this case, this would be something like 2. Again, we need a comma. 3 between 2 numbers here. So we got 2, comma 3. Dash between number and letter. Dimethyl butane. Yeah. So this would be 2, comma 3 dash dimethyl butane. Any questions on that? Now, even if those methyl groups were on the exact same carbon, you would have to give the number twice. Like, let's just say they were both on carbon number 2. You would have to call it 2, comma 2 dimethyl. So that sometimes confuses people. So if they're on the same carbon, you got to give the number twice if it's the same group. And again, this is a situation where we would use both a prefix and also a comma between 2 numbers as well. Any questions on that there? Let's say I had, a little line structure action happening here, dare I say. Here we go. I'll do it too, because I was just drawing. Okay, let's take a look and see what I drew here. I don't know. So longest carbon chain, how many? I see 6, 7. Was there an 8 and a 9 or just a 9? There we go. All right, well, let's see. I'm gonna go start here. This is 1, 2, right? 3, 4, 5, 6, 7. So that is 7. Now, if I come maybe 1, 2, 3, 4, 5, 6, 7, 8, and 9, heading in that direction. I think that's going to win it, to be honest with you. I'm kind of happy I stopped at 9, I suppose. But really, I think your only other option maybe is if you started up here, 1, 2, 3, 4, 5, 6, 7. So it does appear that 9 is going to actually be a winner here. And if I don't erase the actual molecule, that would be good. I'm going to actually leave that there. Just try to, oh, I did. I was 9. I feel like I had something there, and something coming off of there. Yeah, September. All right, I think that's right. All right, so 9 is going to be the base of our name. That's going to be, dare I say, no name. Right, that is 9. All right. Now, when we look at it, we got some groups hanging out here. We got this guy, which is a chlorine, and then we got some lonely lines. Yeah. Where are the lonely lines? What should be at the end of the line, by the way? Yeah. And then that's only one line coming in, which means it probably has 3 hydrogens. So that actually is a methyl group. Yeah. So in line structure, you got a line with nothing at the end of it. It's a methyl group. Any questions on that there? Once again, in line structure, if they want something at the end of that line, they will put it if it's not carbon, right? So if they don't see anything else, it's not. All right, now we need a couple of things here. We have chloral, obviously. We also have 2 methyl groups in this compound, right? So that's going to give us another dimethyl situation happening. So what's left is we need to number that chain. So going left to right here, that would be carbon 1, that would be carbon 2, that would be carbon 3, that would be carbon 4, carbon 5, carbon 6, carbon 7, carbon 8, and carbon 9. So going in this direction, I have stuff at carbon 2, I got stuff at carbon 4, looks like, and I got stuff at carbon 6, right? I got 3 things attached there. Going in the other direction, we'll go blue. This is going to be carbon 1. That would be carbon 2. That would be carbon 3. This would be carbon 4, 5, 6, 7, 8, and 9. So kind of going in the blue direction, it looks like I got something at 4, got something at 6, and I got something at 8. Out of these 2 directions, red or blue, which way should be the right one? It is red. It is the smaller set of numbers. So we are going to go in the red direction. Which means that our chloral group here is going to be at carbon number 2. This other methyl group here will be at carbon number 4, and this guy will be at carbon number 6. So basically putting this together alphabetically, we're comparing the C, and this is what I was talking about before, ignoring the prefix of di, we're actually comparing the M here. So we don't compare prefixes and alphabeticalness. So we're comparing the C and the M. So the C should still come first. So this is going to be a little 2-chloral dash. We need double number here, 4, 6, because they're on each of those carbons. And that's going to be a dash dimethyl. And gonna slap in there a little no name at the end of it. That's a mouthful. No, guess that's what you get when you just randomly draw something. So 2-chloral 4,6-dimethyl nonane. It's all about telling people where you can find everything. That's pretty much what the name means. It means if you start in the back, nonane, you have 9 carbons. And if you go to carbon 4 and carbon 6, they both should have a methyl group. And if you go to carbon number 2, there should be a chlorine hanging there. So that's what the naming's all about. It's just really telling everybody location, 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 where you can find everybody. Any questions on that there? So now that we kind of did the name from the picture, let's do what I think personally is the easiest of all of it, which is actually if they give you a name and they ask you to draw it, it's actually like the most simplest one out of all everything that you would do here. So let's just say we had a name like, let's do Let's do 2-bromyl dash 4-ethyl. And I need enough carbons. Let's go with heptane. Yeah. All right, so let's say we wanted to draw this. Let's just say we wanted to draw the condensed formula. And then we could draw the line structure afterwards if you want. All right, so my recommendation is whenever you have the name and you need to actually draw it, you should always work backwards in the name. So you should always work backwards in the name. And what I mean by that is you should always work in this direction. So what I first see when I go backwards in this name is I see heptane, right? That should tell me how many carbons do I need left. That is 7 carbons. And that is all I'm going to draw to begin with. So I'm just going to simply just draw 7 carbons, leave a little room to fit in some hydrogens and some other stuff maybe. That's where I regret I chose heptane. I think I need one more carbon. I'll put it there. So I got 7 carbons in a row. Good news is, frankly, that takes care of that part of the name. Now, what's left is my groups, right, that are attached. And I know where they're located. I know if I go to carbon number 4, there should be a ethyl group hanging there. And if I go to carbon number 2, there should be basically a bromine hanging there, right? Where is carbon number 2 and carbon number 4? The good news is since you're drawing it, you get to choose. That means you could number left to right and call the carbon on the left number 1. Or if you wanted to, you could call the carbon on the right number 1. And since you're drawing it, you could do either way. I personally, just for reference point, I'm going to call this guy right here carbon number 1. And I'm going to go left to right in my numbering. So right next door would be carbon number 2. Obviously, carbon number 3, carbon number 4, carbon number 5, carbon number 6, and carbon number 7. Not that you need to write the numbers there, but that is the way I'm going to be numbering these guys. All right, so now that I've decided that's the way I'm going to go, obviously I got to stick with it, right? So I'm going to go to carbon number 4 for me, which should be right around here. And at carbon number 4, there should be an ethyl group. Now, when it says ethyl, I know it's a carbon-based group, right? And it has how many carbons? Ethane has 2. Sounds good. So even if you're not sure how many hydrogens it should have, just lay up the 2 carbons at this point, right? So there's my ethyl group coming in, and that takes care of that. At carbon number 2, there should be a bromine. So carbon number 2 should be right next to carbon number 1, and I'm going to put a Br. By the way, it doesn't matter if I put them up or if you put them down. It doesn't matter if you drew up or down. It's all the same. I am out of name at this point, right? But my structure doesn't look so great. Everything else here should be hydrogen. And all I ask to know is carbon needs how many bonds? 4. So if I start here at carbon number 1, that has 1 line coming in, which means this guy's going to need 3 hydrogens, right? The carbon number 2 has 3 lines coming in, 1 on top, 1 to the left, 1 to the right. That means it needs 1 hydrogen to get to 4. Carbon number 3 has 2 lines, 1 here, 1 here, which means it needs 2 hydrogens. Carbon number 4 here has 3 lines coming in, which means it needs 1. Carbon number, I lost track there, 5 needs 2 because it has 2 lines coming in. Next door needs also 2 because it has 2 lines coming in to get the 4. Guy at the end should have how many hydrogens? 3 because it only has 1 line coming in. Now there's my group up on top, which maybe I wasn't sure how many hydrogens. I still do the same thing. This carbon on my group has how many lines? 2, which means how many hydrogens? 2. This guy at the end has only 1 line, which means I need, there it is, drawn condensely. Yes. So this is actually, I think, the simplest thing to do because it tells you basically where to put everything. Again, we're just going to use hydrogen to get carbon to 4. And again, you can just put it in there. By the way, if I wanted to do a line structure like this, I would do the same thing. I would start with 1, 2, 3, 4, 5, 6, 7 carbons. And again, you could choose left to right or right to left. I again will start with carbon number 1 on that guy. That means for me at carbon number 2, I should draw a line and a BR, right? Because that's where the bromine should be. That then would be carbon number 3 here, and that would make this carbon number 4, which again, since this is a carbon group, I just draw something like that. And now I have my line structure basically drawn. And obviously my expanded structure would just be the top guy with all the hydrogens drawn out, basically with lines and stuff like that. Question on drawing something from the name. Why don't you try one here? Why don't you try uh, uh, let's do 2-methyl 3-propyl pentane. Just draw the condensed structure here. While you're at it, why don't you also draw methyl cyclobutane. Okay, so let's take a look. So once again, always kind of work backwards. So I'm going to work backwards. I see pentane, which means I should draw how many carbons? 5. And again, that's all I'm going to draw to start with. Now, again, I can number whichever way I want since I'm drawing it. Again, I'm going to call this guy carbon number 1 for me. Again, if you start at the other end, you can call that carbon 1 if you wanted to. That means if I go to carbon number 3, which is right about here, I have a propyl group, which is how many carbons? 3, right? Based off of propane. So again, if you're not sure the hydrogen configuration, you could just do the carbons at this point. And then I know if I go to carbon number 2, I have a methyl group, which is, I'm going to actually go down because it's kind of crowded there. And that should just be 1 carbon. And it doesn't matter if you go down or up. You could draw it up if you wanted to. At this point, I'm pretty much out of names, which means everything else here is going to be hydrogen until carbon has how many bonds? 4. So guy here at the end will need 3 because it has only 1 line coming in. By the way, the guy down here on the bottom needs 3 because it only has 1 line coming in. The guy above it needs just 1 because it has 3 lines coming in. Guy next to it needs just 1 because it has 3 lines coming in. Next to that guy, 2 because it has 2 lines coming in. And the guy at the end there needs 3. Again, with our propyl group, if you weren't sure, guy at the end would need 3. Guy in the middle would need 2 because it has 2 lines. And this guy also has 2 lines. And there we go. Yeah, so there it is. Any questions on that there? Yeah. Are you asking after you draw it, you wouldn't actually name it what it was named? Yeah, so this sometimes does happen in organic chemistry. If you're given a name and you draw it, it may not actually be the correct name if you actually had the picture first. So it sometimes happens. You're absolutely correct. If you had just the picture first in this case, you would have 6 as your, I think, longest carbon chain there. And it would actually be hexane and stuff like that. But it sometimes happens if you start with the name and then draw it, it might actually end up, if you were going the other way, you would name it the other way. So if you are given a name like this and you have to draw it, that would be the correct drawing for it. But if you're given the formula or the structure there and wanted the name, then it would actually be the hexane and you would follow the same rules we talked about before. But that sometimes does happen when you kind of make up names. Now this one I'm going to work backwards as well. That's a little cyclobutane. Butane's how many carbons? And the cyclo important or not important? It is important. That means that's the one of those ring guys, right? And that's basically means I actually need to put my 4 carbons kind of attached together, right? And in this case, that takes care of cyclobutane. The only thing left is methyl. Where should it go? It doesn't matter. You can put it on any of those carbons you like. And then we could put in our hydrogens. This guy would have 2, that would be 2, that would be 2. Or if you wanted to draw the square like that, right? Now, with a cyclobutane, if you have one thing attached, you do not need a number because wherever it's attached in the ring, it is always going to be carbon number 1. So if you just have one thing attached, you actually don't need a number. If you have 2 things attached, let's just say we started with that and that. Here you would need some numbers because there's 2 things attached. By the way, this would be cyclo what? Cyclopropane, right? As there is 1 carbon, 2 carbons, and 3 carbons, right? Based off of propane, cyclopropane. I got just a lonely line. That is a methyl group. That is a chloral group. So here you do need to actually number where those groups are located because there's more than one. And when we put our groups in, when we name it, we go by alphabetical order, yes? Which means I probably should start numbering out which one, the chlorine or the methyl. Yeah, because that will give the chlorine the smaller number, right? Now I could go 1 here, and I could go 2, 3, or I could go 1, 2, and 3. Definitely want to go that way, right? That's going to give it a smaller number. So that is going to be a 1 chloral, 2 methyl cyclopropane. So if you have more than one group attached in a ring, you do need some numbering. Again, you want to think alphabetically the groups and give that guy the smaller number. If you just have one thing attached, it's basically always going to be carbon number 1 wherever you put it, or wherever it's located will always be technically carbon number 1. Question on any of that there? All right, so let's try a little bit more here. Let's actually go back to the thing we skipped there, which was way back here. So as we talked about before, isomers, right? And isomers basically have the same formula, but different connectivity. So I want you to draw the 3 possible isomers for pentane. And I also want you to name them as well. So name the 3 things that you draw. You could do condensed formula. So we're looking for 3 structures that are different things that still have 5 carbons and 12 hydrogens. So take a few moments there and see what you come up with. And then once you feel like you've drawn those things, lay up some names to make sure. Yeah. I'll give you a hint. The first one is just like straight across. Yeah. It's 5 in a row. Okay, so let's take a look, and obviously here, straight up, first one, we could just roll 5 in a row, right? 4, 5. Obviously put in our appropriate hydrogen, so that one needs 3, this one needs 2, that one will need 2, that will need 2, and that would need 3, so that definitely is hopefully one of them. Now, instead of maybe going 5 in a row, maybe I just stop at 4. Maybe attach the other carbon, say there, and I roll the appropriate hydrogen. So 3 there. This guy would need 2. This guy would need just 1. Would need 3, and this guy would need 3. That's 3, 6, 9, 11, 12 hydrogens. Now maybe I don't go 4 in a row. Maybe I just go 3 in a row. Why not? And put a carbon there in the middle. That one will need 3. That one will need 3. That will need 3. And this guy will also need 3. Guy in the middle has 4 bonds, so he does not get any hydrogens. Yeah. Now, just for extra practice, maybe I go this way. and throw in some stuff because it looks kind of good, maybe. Let's see. Or maybe I do like this, 4 in a row, and just kind of go this way. All right, so I've now drawn 5 different structures. The professional I am, these are all isomers. Are they isomers? So let us see. The way that we know that they're going to be isomers or not is you should probably name them now that you know how to name them. If we end up with different names, provided you name them correctly, I guess is the little asterisk on that. You did draw different isomers. So let's start with the first one here that I drew. That's just straight up 5 in a row. So that's going to be our friend pentane. Yeah. Next one I drew underneath. That is basically 4 in a row. Could also get 4 if you start here and go that way as well, whichever way you want to do it. That 4 in a row is the longest carbon chain with 1 methyl group hanging out. So 4 carbons in a row is butane, right? We have a methyl group, and if I number those carbon, that methyl should end up at what carbon? 1, 2, yeah, 3, 4. If I went this way, 1, 2, 3, 4. Smallest number, right? So this guy should be a 2-methyl butane. That is a different name than pentane, so check, that's an isomer, right? They both have the same amount. They have different connectivities. They have different names. I come up to the guy at the very top. Longest carbon chain is 3, multiple ways. Go straight across, go straight, go up, go straight, go down. And by the way, you could just go in the middle or straight up and down. We'll give you 3 as well. So 3 carbons is actually only propane. I have then a methyl group there, also a methyl group there, and it doesn't matter which way I number it, those methyl groups are going to be on carbon number 2, right? 1, 2, and 3. Guess I should number that guy. That is 2 methyl groups in the same compound. That is a 2, 2, even though they're on the same carbon. I need to give the number twice. Dash dimethyl propane. That is definitely a different name, which means isomer, isomer, isomer. Yeah? Any questions first off on that? Now I had fun and drew 2 extra because why not? Maybe I'll get extra credit if I do that. That is longest carbon chain of this guy is how many? It is 5. 1, 2, 3, 4, 5. Nothing else there. That means this guy is what? What's the name? That is pentane. Is that an isomer? It is not. It's the same as this guy. You just drew it differently. Very common mistake people make. It looks different. It must be. It is not. Yeah. Also, if you like, I'm going to put 1 up, 1 down at the end. Still going to be 5 in a row, even though it looks different. So that's why it's really important when you go to draw isomers that you actually name them correctly. Because if you find yourself with the same name like we just did, you didn't draw an isomer. You just drew something that's the same thing, just looks different, but it's actually still the same compound. All right, so that one's definitely not an isomer. How about this one? Longest carbon chain on the one on the bottom is how many? It is 4. That is butane, right? I have a methyl group here. If I were to number this one correctly, that methyl would be at which number? It would be 1 and 2. Yeah. Or it would be 1, 2, 3. I should always take the smallest way, right? Which means technically this would be 2-methyl butane. Is that another isomer? No, it's this guy. Just turned around, right? You just took it and turned it. Not an isomer either, yeah? So that's why it's important to, after you draw them, you should name them. And if you end up with 2 of the same names, congratulations, you drew the same thing, just looks different. So you want to make sure that you actually do end up with different names. So that's a really good way when you're drawing isomers to make sure that you actually did draw isomers and not just the same thing, just looks different. Because very common people just do that. Instead of going 5 in a row, they go 4 and they just drop the last guy down or something like that. Or they drop the first guy up and then come down and then drop the next guy. But again, if you go to name it, you'll be able to recognize, did you actually draw an isomer or not? Question on Draw correct isomers. Yes. All right. So really, these are the three. These are just duplicates that look different. Yeah. So that is the difference there. Any questions on that there? All right. So, all right, we did some of this, we did some of that, we did some chemistry here. We did that actually. So why don't you do this one? Why don't you draw 3-bromo, 1-chlorobutane, condensed and line structure. See what you come up with there. Yeah, 1, 2, 3, and 4 takes care of that. At carbon number 1, I should have a chlorine, right? So I'm going to call that carbon number 1 for me. Again, you could do it on the other side if you want. Since I call this carbon number 1, that means for me, carbon number 3 would be right about there, and there should be a Br. Everything else at this point is going to be hydrogens, right? So guy at the end has 1 line, so he'll need 3 to get to 4. 3 lines needs 1. 2 lines need 2. And 2 lines here would need 2. That would be our condensed formula. If you're going to do the line structure, basically same deal. Just going to start with the carbons. So 1, 2, 3, and 4. I'm going to call, again, the guy on the left here carbon number 1. So I'm going to draw a line. And I do need to write the Cl, because if I leave the line blank, it's a methyl group, right? So it'll become a methyl group. So you do need to put the Cl. That's carbon number 1. That would be carbon number 2 for me. Carbon number 3 would be right about there. And I would need a bromine, right? And that would be that. Any questions on those there? All right. So why don't you give the names for these two, I think? Maybe. There we go. Okay, so let's take a look again on the first one here. We're just going to count carbons 1, 2, 3, 4, and 5. There's really no other options and stuff to go kind of straight across. So 5 carbons should give us a base of pentane, as they're all single bonded. That would mean we have just a chloral group here hanging off of it. And you can probably recognize that perhaps numbering right to left here will give that chlorine obviously a smaller number if you went left to right. You're looking at like carbon number 4 if you went this way, right? 1, 2, 3, and 4. So that would be the way we would want to go with a smaller number. By the way, once you lock in the numbering, you do have to keep the numbering for everybody that's there, so you can't go one way or the other. So that would give us a 2-chloral pentane in this case. Questions on that one there? I think on this one, there's a multiple ways you could get there, but I think 1, 2, 3, 4, 5 is still the longest. You could actually start here, I think, and kind of come around, and you'll get 5 as well. But 5 seems to be the longest, and again, that's going to give us pentane as the base of the name. That means that we do have these 2 lines with nothing written there, which means each of these lines are methyl groups. And since there's actually 2 methyl groups in this compound, that's going to give us a dimethyl that's happening. So if we number this, once again, you can probably see, hopefully, if you go left to right here, 1, 2, 3, 4, 5, as opposed to if you go 1, 2, 3, 4, and 5. So going in this direction is going to give those groups a smaller number. Remember that we do need to give the number twice here. So both numbers, 2, 3, and we need that comma between dash dimethyl and pentane. Any questions on either of those names? Question on how to name alkanes, draw alkanes, cycloalkanes, any of those things. All right, so I'm just gonna kind of go a little bit ahead a little bit and talk about a few things here to finish up with here in the last 10 minutes. And I'm gonna talk about 2 other sort of functional groups that are related to sort of alkanes. And those are alkenes. And alkynes, Y-N-E. All right. So alkenes, the functional group is a carbon-carbon double bond is the functional group. Well, for alkynes, it's a carbon-carbon triple bond is the functional group. And for reference, as we've been talking about alkanes, they basically are the ones there with carbon-carbon single bonded, basically as their functional groups. So the way that we go about naming these guys are pretty straightforward. They will still be based on the longest carbon chain. What you're looking for, though, is the longest carbon chain needs to have either a double bond in it or a triple bond in it. They do have, for the alkenes, a general formula CnH2 times N. It will lose two hydrogens because it has one double bond. The alkynes have CnH2n minus 2 because it makes a triple bond, which is basically a double bond and a triple bond. It will lose a total of 4 hydrogens, so that's why you subtract 2 in this particular case. So when we look at something, for example, like this, let's put a Cl there, and we'll do like, I don't know, and we'll put double bond there. Let's go with a 2. And let's just say we had pretty much the same deal. Except that I do need to get rid of that hydrogen there in the middle. Right, that guy there. Now let's just say this, right? So when we go to name these guys that have obviously a double bond or a triple bond in it, there are a couple of things that are similar and a couple of things that are different than what we do with alkanes. So the first thing that's similar is we still are going to be looking for the longest carbon chain. As I mentioned before, it does need to contain either the double bond in it or the triple bond. So you can't go around those bonds. They have to be in it. So in this case, if we were to roll through this, that is 1, 2. That's not so good. Again. That is 1, 2, 3, 4. So when we count the longest carbon chain, and obviously that does contain the double bond, it still goes back to the alkane name. So for carbon and an alkane is bu. But since this has a double bond, ENE, yeah. So instead of butane is butene, yeah. All based off of those first 10 alkanes, like I said, right? Just change a little bit of it as you go to these different organic groups. Now, also different is this. If you remember when we numbered everything, right? When we did alkanes, the thing that took the priority in numbering to give them smallest numbers were the groups. That changes when you have a double bond or a triple bond. It's actually the double bond or triple bond that takes the priority in numbering. So when I go to number this, which way should I number that gives the double bond the smallest number? I would need to go left to right. Because if I go left to right, the double bond is located at carbon number 1, right? If I go right to left, or not good. I need to go in this direction because the double bond takes the priority here, and I need to get it to the smallest. Also different is, if you remember, organic chemistry naming is all about telling people where things are located. Whenever there is more than one option as to where the double bond or triple bond could be located, which is typically speaking about 4 or more carbons that occurs, you have to give the number as to where the double bond's located. So in this case, my double bond's located at carbon number 1. This would be 1-butene. The 1 is the location of where the double bond is at. That is the double bond location. Any questions on that? Now the rest is exactly the same because I locked in my numbering for this. My group, which is the Cl, has to be a carbon number 3. So this would be 3-chloral-1-butene. Again, the double bond's located there. The reason you have to do that is if I drew this, now when I look at it, still has 4 carbons and a double bond, which means this guy is still butene. Now, if I number left to right, my double bond is now located at carbon number, it starts at carbon number 2. If I number right to left, my double bond starts at carbon number 2. Doesn't matter which way I go, left to right or right to left for the double bond. It doesn't. They're both at carbon number 2. So this, by the way, is 2-butene because the carbon double bond is located at carbon number 2. By the way, if you had to take a guess, because it's a tie for the double bond, what next should be most important? Where the Cl is located, right? And which way gives the Cl in this case the smaller number? It is actually numbering in this direction. So we do look at the double bond first, but because it's a tie, no matter which way you go, the next important thing is the group. And the group gets the smallest number going right to left. So this should be 2-chloral-2-butene in this case. And that's why we have to give the number for the double bond, because in the second one, it's at carbon number 2, but in the first one, the double bond's over at carbon number 1. So you have to tell people that. First off, any questions on that? By the way, the triple bond works the same way. If I put an H in there, that would be good. There we go. So when we look at this, it has 4 carbons, which is still based off of butane. We're going to scratch out the butane because it has a triple bond. Those end in YNE. So this is what is known as butene, YNE, yeah, because it's not butene, because that would be a double bond, and it's not butane, which would be all single bond, right? So again, they're all related to each other, just changing a little bit thing. The triple bond location is going to be the most important here, and it's at carbon number 1, right? Again, if you went in the other direction, it would be at carbon number 3. So carbon number 1 is the way we want to number. This would be 1-butyne, and that means my chlorine here would be 3-chloral-1-butyne. So if you have an alkene, which is a double bond, or an alkyne, which is a triple bond, you number it the same, or you basically find the longest carbon chain containing the double bond or triple bond. The priority in terms of numbering goes to either the double bond or triple bond. If you end up with a tie like we did on that other one, then the next important thing is the groups that are attached to give those guys the smallest numbering. Everything else sort of works the same way. Any questions on that there?